In this video, we're going to go through the basics of Lewis structures and how we can draw the Lewis structures for any compound in a way that minimizes formal charge. So as we go through this, it's important to remember that the best Lewis structure minimizes formal charge. Okay, so I'm going to read through the rules, and they might seem like a lot, but once we get through some examples, I think the rules will make sense. So, first thing you're going to do is you're going to count all your valence electrons. Okay, don't forget to take into account the charge of your compound, then compounds with charges will have brackets. You're going to connect all your atoms together with bonds. A bond is represented by a line, and a bond represents 2 electrons. Okay? The atom that can form the most bonds typically goes in the middle, and if there is more than one atom that forms the greatest number of bonds, then atoms that form the greatest number of bonds get bonded together. A lot of the time, the one unique atom is going to be your central atom, even though that does not form the most number of bonds. Okay, and then it's important to remember that hydrogen's always going to be a terminal atom, meaning it will never be a central atom. You're going to give lone pairs to each element so that they all have 8 electrons. Hydrogen, because it's in the first energy level, does not get 8 electrons. Okay? You're going to count your electrons, and most often your count will be too many. So if it's too many, you're going to remove 2 lone pairs and insert a multiple bond until your count matches the correct number of valence electrons. Okay? And then if your count is too few, then you're going to add a pair of electrons to your central atom. If your count is too many by 1, then take an electron away from the least electronegative atom. And NO2 with no charge is an example, but I'm not going to be worried about that in this video because those are very, very rare. That'll give you the general structure of your Lewis structure, but you always need to take into account formal charge. Formal charge is where atoms that might be holding charges will move around their electrons to minimize charge. So for example, if there's something with a positive 1 charge next to something with a negative 1 charge, they might share in a pair of electrons to minimize their charge, and we'll see how that works. Now, formal charge only happens when your central element is in the 3rd energy level or lower. Okay, that's kind of a nice rule to know. And then what you'll do for formal charge is you'll divide each bond line in half and then count the number of electrons that the atom has, and then compare this number to the electrons that the atom typically has according to your periodic table. And all formal charges must add up to equal the overall charge of the compound. When you do formal charge, if you have a negative formal charge next to a positive formal charge, then atoms will form a multiple bond to minimize the formal charge only if the atom with a positive charge can accept another bond, meaning it's in the 3rd energy level, 4th energy level, 5th energy level, so on and so forth on the periodic table. To do this, you'll remove an electron pair from the atom with a negative formal charge and create a multiple bond between the 2 atoms. You do not erase a pair of electrons from any atom. You're just moving electrons because your valence count is good at this point. So let's see how this works. Okay. We are frozen here, so what we're going to do is close out just for a second. And we're back. Okay. So give the best Lewis structure for each of the following compounds, and you'll want to write in pencil because we'll do some erasing. So the first thing we're going to do according to our rules is add up the number of valence electrons. So nitrogen is in family 5A, so it has 5. Oxygen is in family 6A, so it has 6. And then a negative 1 charge means that we have an extra electron, and so when I add these up, I get 18 electrons, so that's how many I need to have in my structure. Nitrogen, with it having 5 valence electrons, it typically forms 3 bonds to get up to 8 valence electrons. It's called the Octet Rule, where oxygen has 6 valence electrons, and so it typically forms 2 bonds to get up to 8 valence electrons, and so our central element is going to be nitrogen because it forms the most number of bonds. We're going to bond oxygen to it, and we're going to go through and we're going to give every element 8 electrons. So it's important to know that a bond consists of 2 electrons, and so right now oxygen has 2 electrons over here because if it's in a bond, it's really sharing those electrons, and so we'll add 3 more pairs. Some people like to think that each of the 4 sides of an element needs to have either a bond or a lone pair. We'll do that to nitrogen. We'll do that to oxygen, and then we're going to count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Right now we have 20, and that's no good. How I would typically count is I count by 2s. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And that seems to go way faster than by counting each individual element. So what do we do when our count is too many? We're going to erase a pair from a central atom, and then pick any of our terminal atoms and also erase a pair. And then form a multiple bond between the two, and then we're going to count to make sure we're at the correct number. 2, 4, 6, 8, 10, 12, 14, 16, 18. That is our count. And we're going to put a bracket around our structure because it has a charge, so we put a bracket with a -1, and that is our structure. We don't need to worry about formal charge. It does have a formal charge, but we don't need to worry. I'm going to call formal charge Fc because our central atom is in the second energy level. Okay, and we talked about that only elements in the third energy level or higher, meaning third, fourth, fifth, sixth, seventh, can expand their octets or have more electrons or change their formal charge. So this does have a formal charge, it's just that we can't change it. Okay, let's look at number 2. Carbon is in family 4A, so it has 4 valence electrons, plus hydrogen is in family 1A, and there's 4 of them, so we get 8 valence electrons. Carbon is going to be our central element, and whenever you have carbon, that will be your central element. Okay, and we're going to bond hydrogen to it. Carbon has all 4 sides covered, and then actually hydrogen is the one exception. We don't give hydrogen an octet, and so we're actually ready to count. 2, 4, 6, 8. Each bond has 2 electrons, so that has 8 electrons. And so this is actually our structure. We don't need to worry about formal charge because carbon's in the second energy level. And we're good. We don't need a bracket because CH4 is methane and that does not have a charge, so we don't need any brackets. Okay, let's look at number 3. Carbon has 4 valence electrons. Hydrogen has 1, but there's 3 of them. And then fluorine is in family 7A, so it has 7 valence electrons. When I add this up, I get 4 plus 3 is 7. Plus 7 is 14 valence electrons. Carbon will be my central element. I'll bond 3 of my hydrogens around there, and then my 4th bond will actually be for fluorine. I give every element except hydrogen 8 valence electrons. Carbon already has all 4 sides covered with a bond, so it has 8 electrons. So I'm going to give fluorine 3 lone pairs. Then I'm going to count 2, 4, 6, 8, 10, 12, 14. My valence count is good. I don't need to worry about formal charge because my central element is carbon. C2H4, this is called ethane, or ethene actually, ethene. And carbon has 4 valence electrons plus hydrogen, which has 1 valence electron, so we get 8 plus 4, which is 12. Now, what do we do when we have 2 carbons? That means we have 2 central elements. So we bond it like this, and the best strategy I have is just to use symmetry. So to give each carbon just 2 hydrogens, and then give every element 4 valence electrons except, or 8 valence electrons except hydrogen. So we give 2 lone pairs to each carbon for all 4 sides to be covered, and then we're going to count 2, 4, 6, 8, 10, 12, 14. Well, right now I have too many valence electrons. So what I'm going to do is erase a pair from the central elements and just add a multiple bond between them. And then when I count, I get 2, 4, 6, 8, 10, 12. And that is the correct structure. I don't need to worry about formal charge because my central elements are in the second energy level. Okay, let's do a few more. We have arsenic pentafluoride. Arsenic has 5 valence electrons. We have 5 fluorines, and they each have 7, and so we get 35 plus 5. We have 40 valence electrons, and man, is that a lot. So our central element is going to be the atom that can form the most number of bonds, which is typically going to be our unique element. So we'll have arsenic be our central element, and then I'm just going to bond my fluorine atoms around my central arsenic atom. I'm going to give everything 8 valence electrons. And I'm going to count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So my count is good, but what do I do when my central element is in the third energy or lower? That means I really need to focus on formal charge. Okay, there's lots of ways you can do formal charge. This is just the way that I do formal charge, is I'm going to slice all my bonds in half. And when I slice them in half, I'm going to act like one of the electrons went to fluorine and one went to arsenic. Okay, so I might draw a picture that looks kind of like this. And then I'm going to compare the amount of valence electrons that I see to the amount that they typically have, which would be these numbers up here. Arsenic typically has 5 valence electrons, and fluorine typically has 7. And so I'm going to count, and I'm going to say fluorine has 1, 2, 3, 4, 5, 6, 7. Well, it has 7 in that picture, and it normally has 7, so that would be a charge of just 0 because there's no difference. And that's going to be the case for all of these fluorines. I'm going to go ahead and I'm going to do the same thing for arsenic. Arsenic normally has 5, and in this picture I see 1, 2, 3, 4, 5. And so there's no change from what it normally has, and so that would be a formal charge of 0. And all of the formal charges should add up to be the overall charge of the compound. And so if I add up all these zeros, 0 plus 0 plus 0 plus 0 plus 0 plus 0 will give me an overall charge of 0, which is what I have in ASF5. Okay? And the best Lewis structure is the one that minimizes formal charge, meaning that gets us as close to 0 as we possibly can. And so this is a very stable structure because we have completely minimized our formal charge. Let's look at So3 Sulphur Trioxide. Sulfur normally has 6 valence electrons. According to the periodic table, it's in family 6A. And then oxygen also normally has 6 valence electrons. And so since sulfur is our unique atom, we're going to put it in the middle. And we're going to add these together, and we get 24 valence electrons. We're going to bond sulfur to oxygen, and then we're going to give every atom an octet or 8 valence electrons. So we go through and we do something like this. Don't forget to do that to your central element. And so we add 2 lone pairs to sulfur. And then we're going to count, and it looks like I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So right now I have too many valence electrons. Okay, I have 26, and that's no good. So what you do when your count is too many, you erase a pair from the central element, and then pick any of your terminal elements. So I'm just going to pick this top oxygen and do erase a pair. And from those 2 pairs, you just form a multiple bond between the 2 atoms. And then let's go back through and count, make sure we've gotten our count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So our count is good now. And because sulfur is in the third energy level, you need to worry about formal charge. And so here's how we do formal charge, is we slice all of our bonds in half. And we say, okay, let's compare the amount of valence electrons that I see in this picture to the amount that it normally has. So I'm going to go through, and sometimes it's helpful to draw in the electrons that you see that you've sliced in half. And you would say, well, sulfur normally has 6 valence electrons, and right now in this top oxygen, I see 1, 2, 3, 4, 5, 6. 6 minus 6 would be 0, so that's a formal charge of 0. In this right oxygen, I see 1, 2, 3, 4, 5, 6, 7, and so that means I have one more electron than I normally would have. Okay, electrons are negatively charged, so that'd be a -1 formal charge. When I go through and I do this next oxygen, notice it's bonded the exact same way, so when I count, I have 7, and so that would be one more than what I normally have, so that would be a formal charge of -1. And then let me do the central sulfur. Sulfur normally has 6, and right now with the bond sliced in half, I see 1, 2, 3, 4, so it's missing 2, so that would be a +2 formal charge. Overall, SO3 needs to be neutral, and it is. Even though I have charges within the molecule, it is neutral. Okay, and that's because +2, -1, and -1 add up to be 0. But what our rules say is that if I have a positive formal charge adjacent to a negative formal charge, then the atoms will form a multiple bond to minimize that charge. And so what happens is I've already got the correct amount of electrons. And so what happens is my negative atom is very generous and just takes those electrons and moves them and creates a bond. So I took 2 electrons here and I just moved them to create a bond. So I didn't permanently get rid of, and I didn't permanently add any electrons. The amount of electrons stayed the same. And what this does is if I go back through and I count the formal charge, 1, 2, 3, 4, 5, 6, oxygen normally has 6 valence electrons, so that's a formal charge of 0. Sulfur has changed, so I need to count 1, 2, 3, 4, 5. Sulfur normally has 6 valence electrons, so that's only a +1 charge now. So I've minimized it a little bit. And I'm going to keep going until I get a formal charge of 0. Okay, so I still have a positive next to a negative, and so this can keep going. There's still an attraction. So what's going to happen is my negative atom is going to take a lone pair and make a multiple bond there. And so I get 1, 2, 3, 4, 5, 6. Oxygen normally has 6. That's a formal charge of 0. Sulfur has a valence count of 6, and now I have 6 there, so that's actually a formal charge of 0. And so what the overall structure looks like, if I want to clean this up, is it looks something like this. And every atom has a formal charge of 0, and this is the best Lewis structure because it minimizes formal charge. Okay, let's see how this works with SO3, and it's going to just take some practice to get used to, and then you should be rolling. The valence count in SO3 is 6 plus 3 times 6, and then plus 2 at the end, and when you do that, you get 26. I'll put sulfur as my central element, bond my oxygens around, 1, 2, 3, 4, 5, 6. And I get something that looks like this. I'm going to go through and count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So my count is good. And I'll put a bracket on it. And if sulfur was in the second energy level, I wouldn't have to change anything. But sulfur is in the third energy level, so what I need to do is worry about formal charge. When I worry about formal charge, I slice all my bonds in half, and I compare the amount of valence electrons with the bonds sliced in half to the number that the periodic table says each element has. So, oxygen normally has 6, and right now it has 2, 4, 6, 7. so that would be a -1 formal charge. And all of these oxygens are bonded in the same manner. Sulfur has 1, 2, 3, 4, 5. Normally has 6, so that's a +1 formal charge. There is an attraction going on between the +1 and the -1, and you can pick any of your oxygens. Oops. And so what we'll do is we'll just pick this bottom oxygen, and when we do this, we erase a pair, but we don't permanently erase a pair, we just create a bond with those two electrons. And then now we're going to go through and we're going to count. We've got 1, 2, 3, 4, 5, 6. Oxygen normally has 6, so that's a formal charge of 0. And then here we get 1, 2, 3, 4, 5, 6. Sulfur normally has 6 valence electrons, so that's a formal charge of 0. Notice that we're still overall, we're always going to be at this -2 formal charge no matter what. We're just trying to minimize the charge within the molecule. We're actually done with this structure now because we no longer have a positive atom adjacent to a negative one. And so our final structure looks something like this. Okay, and that is sulfite. The last one we'll do here is sulfate, and this is one I would just know because it shows up a lot. Sulfur has 6 valence electrons plus 4 times 6 plus 2. We should get 32 valence electrons here for sulfate. Sulfur will go in the middle, will bond all these oxygens around and give everything 8 valence electrons. And when I count, I get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. My count is just fine. But I do need to focus on formal charge since sulfur is in the 3rd energy level, so I'm going to slice all my bonds in half. And when I do that, I see that oxygen has 7 when it normally, according to the periodic table, has 6, so that's a -1 formal charge for all my oxygens. Sulfur, I can see it looks like with the bond sliced in half, it has 4 valence electrons. According to the periodic table, it normally has 6, so that'd be a +2 formal charge. Since sulfur is in the middle and it has a positive charge, oxygen's on the terminal ends and it has a negative charge. That means that there is an attraction. And so pick any of the oxygens, and a lone pair is going to be moved from being a lone pair to a bonding pair. That changes this oxygen's formal charge to 0 because 1, 2, 3, 4, 5, 6, and that matches its valence count. That changes this sulfur to +1 because 1, 2, 3, 4, 5. And so I'm going to keep going because I have a positive next to a negative, and you can pick any of these negative oxygens. It does not matter. And I'll pick the one on top. I'm going to erase a pair, but I'm not permanently erasing a pair. What I'm doing is just moving those lone pairs and creating a multiple bond. That changes my oxygen to formal charge of 0, my sulfur to a formal charge of 0. And now I'm actually done because I no longer have a positive atom next to a negative atom. And so my final Lewis structure looks something like this. And then I'll put a bracket on it. And this is what sulfate looks like. And a question you may be wondering is, could you have put a double bond there instead of there? Or could you put a double bond there instead of there? And absolutely. When you have options as to where you put your double bond, that means you have resonance. So this has resonance. Sulfite has resonance. So3 does not have resonance because I did not have an option where I put my double bonds because I was going to end up with double bonds everywhere. There's no double bonds in ASF5, so no resonance there.